Hello everyone, I'm Ian Zhao from Georgia Tech. I'm going to present our work, Boosting Ensemble Accuracy by Revisiting Ensemble Diversity Metrics. Here's a GitHub link. We typically use all available base models to build an ensemble team. The question is, can we find a smaller ensemble with better ensemble accuracy? The right table presents the model pools for Sufferton and ImageNet. For each dataset, we need the two example ensembles on the top left table. They achieve higher ensemble accuracy than the best base models with a lower cost, that is much smaller team size. So the next question is, how can we find such high accuracy and low cost ensembles? We propose FQ ensemble diversity metrics to solve this problem. Let's first look at what FQ diversity metrics are and why we need them. Here, lower FQ diversity scores corresponds to higher ensemble diversity. The top left table shows 5 ensemble examples. QCK gives the two high accuracy ensembles, marked in yellow, a diversity score higher than the threshold, and thus fails to identify them. Our FQ diversity matrix will compute different diversity thresholds for ensembles of different sizes. It successfully identifies the ensemble 0 to 7. The other high accuracy ensemble, 0 to 357, can be identified by another FQ diversity metric, FQKW. On ImageNet, we observe similar observations. FQ diversity metrics show close correlation to ensemble accuracy, which can effectively identify high accuracy ensembles. The goal of this study is to design diversity metrics to guide the selection of smaller ensembles with high ensemble accuracy. We propose 6 FQ diversity metrics, including 3 pairwise and 3 non-pairwise metrics. Here are the general steps to use FQ diversity metrics for selecting high-quality ensembles. FQ diversity scores involve two-step computation. For example, for the ensemble 1, 3, 4, 6, 7, we first compute the FQ scores and thresholds for each focal model. Here, this ensemble is selected by focal model 4, 6, and 7. Then, we normalize these scores across 126 teams for each focal model for the next step combination. Here are the detailed steps. With the normalized scores, we perform weighted averaging to obtain the unified FQ score. Given this score is higher than the FQGD threshold, this ensemble will be pruned out. Meanwhile, different FQ metrics will give the different ensemble selection results. For example, the ensemble 01567 is selected by FQKW, while FQGD will prune it out. This observation motivates our EQ diversity to combine top-performing FQ diversity metrics to further improve the ensemble selection results. We evaluate our FQ-EQ diversity ensemble selection on Sufferton and ImageNet. On Sufferton, first, FQ diversity can effectively select high-quality ensembles and prune out low-quality ensembles. Second, EQ diversity ensemble selection achieves the best performance. In the middle table, we list the 5 example ensembles. The first low-quality ensemble is pruned out by EQ. The other 4 high-quality ensembles are identified by EQ. On ImageNet, FQ has a very high probability of choosing high-quality ensembles. That is close to 100% for FQBD, KW, and GD. The middle table shows the number of ensembles that are uniquely identified by these FQ diversity metrics. Different FQ diversity metrics may select different ensemble teams, making the combination of several top-performing FQ diversity metrics very effective. That is our EQ diversity ensemble selection. Our FQ-EQ diversity metrics can be effectively applied in many computer vision tasks for obtaining high-performance ensembles. We further visualize several ensembles via a few image examples. Even though the best memo model of an ensemble team fails to give correct predictions, the ensemble teams selected by our FQGD can still generate the correct predictions, repairing the best memo model mistakes. That's all. Thank you for your listening.